Okay, I think we're gonna start the class. So today, basically, we're going to talk about cylindrical coordinates. And if we have time, start spherical coordinates, and those are like the last two things for the exam. So let me, like definitely we'll be done by Monday of next week. So let's see. Cylindrical coordinates is actually not too bad. So let's start with those. The way you should think of them is as polar coordinates with the z-axis. So think of them as polar coordinates plus z-axis. By that, I just mean that if you have like x, y, z, and you take like a point here, x comma y comma z, then in cylindrical coordinates, you can imagine that this point like has like a shadow on the xy plane, right? Which is just essentially the point that you get by forgetting about the third coordinate, right? So to this point, since it's on the xy plane, you can apply like the usual polar coordinate variables. So like there's like this radius r, and then this angle theta. And so x continues to be, x is still r cosine of theta, and y is still r sine of theta, and z remains z. So there's nothing that you do to z. So z remains the same. Okay, so you can think, in fact, in the context of cylindrical coordinates, this r, you can think of r as like the distance of a point to the z-axis. So r is still root of x squared plus y squared. And that can be, but now if you look at this picture, it now represents the distance of a point to the z-axis. And the angle theta is still, the tangent of theta is still the y over x. Is that okay? Is that making sense? So I'm just saying that basically what we're going to do today is like start with polar coordinates, but now you keep track of a third variable, which is z. but you're not doing anything interesting to Z, so it's still the same. So essentially we're doing again polar, I mean, think of this as polar version 2.0, because like the bounds are going to be found in a very similar way as we did in polar coordinates. So far so good. Any questions? R is not constant. R is it's like it's like the R of polar coordinates. So it can vary because like it depends on X and Y, right? In the same way in which theta is, well, Z is not constant either, because Z represent, like, you know, you could choose points at different heights. So it would be like, well, let's do like you know, Z could like, you know, if you choose Z like just to give you an example, two concrete examples. So if you have like a point here, yeah.
Professor, one question. So when you say like Z remains the same variable, do you mean like it doesn't change into like a trig function?
I mean that you're not changing it in terms of, you're not like, you know, in the, like, you know, when we did polar coordinates, we got rid of X and Y, right? Because we changed everything in terms of R and theta, right? What I'm saying, but what I'm saying here is that when you see something with Z, you still leave it in terms of Z. You're not trying to convert Z in terms of anything else.
Okay.
So for example, like, you know, like this is like what I mean. Like, remember that this in polar became R equals 2. Is that okay with everyone? Now, if you had something like this, now in cylindrical, what happens here, like x squared plus y squared, you still change them as their versions in polar coordinates. So it becomes r squared, right? But z remains z, so it just z squared. So that's how that this becomes in cylindrical coordinates. So this is like, is this more better now? So I'm just saying, like, you don't do like the point is that you don't have to change, you are not trying to change Z in terms of anything new, which is what happened with X and Y, where we are replacing X and Y with their versions in terms of R and theta. Like,
I'm sorry. One question. Why are we changing it into polar?
oh, just because like like, you know, it's just that certain integrals just become easier if you do like a combination of like the reason is like the same reason that we use polar at the beginning, right? Why did we use polar coordinates for some double integrals? In principle, it is because some integrals become easier. So the logic for like doing cylindrical is similar. Like the thing is, like if you use Cartesian like dz, dy, dx, some will just end up being harder. But if you switch them to polar, I mean, sorry, to cylindrical, they just simplify a little bit. So it's just like a simplification scheme. The next coordinates that we will use are called spherical, and in spherical you sort of like do change both the x, y, and z in terms of new stuff. But for now, this is sort of like an intermediate step between Cartesian and spherical, because we're just changing 2 of the 3 variables, if that makes sense. But it is just for like in principle, because some regions of integration, like just like the bounds are easier to find in cylindrical coordinates. Is that okay? So
yeah. But why does Z still not change though?
well, because I mean, it is sort of like cylindrical. Will be helpful for cylinders. Yeah, like in fact, the next example will be about that. But you could say, but you know, there will be a next change of, like after cylindrical, we'll do spherical where the three change. So it's not that, I mean, there will be occasions where Z also changes. It's just that you don't necessarily want Z to always change all the time. That's what I'm trying to say. It's like like it's just there like there are like things that like do have some sort of like cylindrical symmetry. So if you want to call it like that. So like cylinders are like a thing in nature. I like look at all the, you go to a supermarket and you see a bunch of cylinders in the way of cans of drinks, right? So I mean cylinders make sense for that reason. So no, like containers, you know, everything, a lot of things if you think about it are like cylinder based. So so it does sort of make sense to leave it Z alone, because you'll see that in a moment that sort of interacts nicely. Yeah, like okay, like right, like for example, oh, I'm about to do it, like I'm about to do like a cylinder example, so we'll do it there. But is it now better, more clear now that like why Z and it's not necessarily, it is a variable. That's what I'm trying to say. It's not like a constant. Like it's just that you're not replacing it with anything new. So like just to put this in parentheses, like here I meant like not changed, not being changed with in terms of new variables. Okay, and then the last thing that you need to know is that what happened with dv, right? This was the stuff that goes into the triple integrals from before, like dz, dy, dx, right? But now remember that dz, like dy, dx, you could just think of as dA when we were doing like polar coordinates. Sorry, or double integrals. But what was the formula for dA in polar coordinates? Good. So this is dz r dr d theta. It just looks a little bit weird to have the r sort of you know, in the middle of two d's. So you put it like in front. So you write it as r dz dr d theta. And so the takeaway is that in cylindrical coordinates, dv is r dz dr d theta. Okay. Is that okay? Is that so you're saying like like, well, it was just because if you look at the, let's see, how long ago did we do the polar let me let's go to GeoGebra. Here it is. It sorry, just to show you this quickly. So it is like if you look at it in it was just that we did like you know, we sort of had to approximate the area of this thing, and so this arc was r d theta, and then you sort of move it by some length dr, and so like, you know, it was almost like a rectangle, this quantity, not quite like a rectangle, but it can be approximated sort of like with the area of some sort of rectangle. So like one of the sides is r d theta because it's like the length of an arc of a circle. So that's how you get r d theta, and then you have to move this length by some amount dr, and that's how you get r d theta times dr.
Okay, that makes sense. They're like pizza slices, right?
Sorry.
They're like little pizza slices.
Yeah, exactly. The other thing that I had said was that like you can also, I mean, that's less of an argument, but it's still sort of useful to sort of find the right answer. You know, dV is supposed to have units of volume, right? Let me just erase for a second the R here. What units do you have thus far? dz has units of length, dr has units of length, d theta has no units because it's in radians. So this has units of area, right? And you use the R factor to sort of get units of volume.
Okay, thank
yeah,
you.
Yeah,
That was
that's like it's, I mean, at least helps you try to find like the correct speculate on what the correct answer should be. But the point is that, so when you see triple, like this is what I was getting at. What are you going to see? So how does like a triple integral in cylindrical look like? You have something like this. I mean, it's still like a triple integral. Here you have some function f, but you are going to have this r, dz, dr, d theta. Okay. And the rules of the game are sort of similar to before. Like, so if you integrate first with respect to z, right? That means that you're going, it is the same as before. So as how I taught you last time to do triple integrals in Cartesian. So we're still going to draw arrows which are parallel to the z-axis. So here, like you use so here you use arrows parallel to z-axis. And so this is like where what you have to put here is like the equation where the arrows enter, right? But now the equation has to be written can be written in terms of r and theta, because those are like the two variables that you were not using. So this is like, it can be in terms of r and theta. And the other one is the equation where the vertical arrows exit. So let's put it here. And again, this equation can still be in terms of r and theta. And I don't know if you remember, like in triple integrals last time, how I told you you had to do like these 2 bounds. Like you were supposed to look at the shadow on the XY plane, right? So here you look at the shadow on the XY plane. But now the bounds like of this shadow are written in polar coordinates, not y and x, right? But now write the bounds. The bounds are written in polar coordinates. Is that okay? So let's do an example so that you see how this works. So let's use this to find a volume. Okay. So let's try to picture this first. Okay. So we're looking at something that's above the XY plane. Well, the cylinder, like, it's like, you're not trying to find the volume of the cylinder per se. It enters into what the volume is that you're trying to find, but you have to draw everything that the region refers to. So, for example, let's just go one by one. Like this is saying that you're looking at stuff above the XY plane. There's nothing here much to do in this picture. Then you have this cylinder. What is this cylinder? Well, I mean, you would say, well, this is really the equation of a circle, right? Center at 0,1 of radius 1. So here you have 0,1. Right, like you would say, yeah, like just like sort of the cylinder is the most important player, but you also need the plane. Like the last equation, the second equation is also important. So you would say, okay, this is like that circle, this circle, right, on the XY plane. But remember that this is like a cylinder now because Z is not involved here. So you sort of, for each value of Z, you can sort of draw the same circle. So you could get like, you draw the same circle here. Is that making sense for why that's a cylinder? Because you just get like a copy of the circle on at each height, basically, at each value for Z. So that's how that cylinder looks like. So this is a cylinder x squared plus 1 minus y squared equals 1. Yeah, it's just a, right, exactly. It's a bunch, yeah, of pepperoni slices stacked up. Correct. Good. And then what's the plane Z equals Y? Again, why is that a plane? Well, strictly speaking, that's like a line, right, on the YZ plane. So on the YZ plane, you sort of draw a line which is at 45 degrees, which is this one. But again, it's sort of the same principle where you have to copy this line everywhere else. So you get, for each value of X, you sort of draw the same line. And so that's how you end up getting the plane. Is that making sense? Oops. So if you want, let me show you this in GeoGebra. Here it is. So you see, this was the cylinder that I drew, the red one. I guess it was orange in the picture, but right. And then there's this plane, which was in blue. And then you see, like, there's some volume that's above the floor level, about this XY plane, and that's inside is trapped in that can, right? So it's like if you had taken like a can and cut it, right? Like you sort of slice it, but you do not slice it. You do like it's tilted. Your cut is slanted, so it's not like the cut is not like parallel to the XY plane. It's rather you it's like like a magician's show, but like the cut is like just with some angle. So that's how, and then you get like everyone sees the volume. It's like just like the stuff between the two planes and inside the cylinder. Is that making sense? Yeah, good. Can everyone visualize it?
Yes.
Good. So let's go back to the picture. So like in these problems, again, like whenever you have equations, you should like rewrite them first in terms of polar coordinates or cylindrical coordinates, right? So because those are the ones we're going to use. So how would you write the first equation, like the blue equation, in terms of cylindrical coordinates? Remember, that's just what you get by changing y in terms of polar. So you get as z equals r sine of theta. Because you're supposed to leave a z alone. So the equation of the plane in cylindrical coordinates is just z equals r sine of theta. Is that making sense? Now, this one is a little bit more interesting, because like, again, now you have to write it in terms of cylindrical coordinates. There's no z involved, so basically what you're going to do is write this in terms of polar coordinates, right? So before, how would you rewrite this in terms of polar coordinates? Well, one thing you can do is like just expand out the expression. And then what does this become? X squared plus y squared becomes r squared. And this becomes 2r sine of theta. So the equation of this cylinder is, or circle, basically is 2 sine of theta. Is that making sense?
Could you also divide both sides in the r squared step by 2 to get an expression for z?
Like here you're saying dividing by 2.
Yeah,
Well, if you did like if you like you say like just to get r squared over 2.
yeah, because then you would have equals r sine theta, and that's equal to z.
Oh, okay. I see what you're saying, but yes, that's equal to z, but only when they are intersecting one another, right? I mean, like if you were trying to, like this is well, sorry, first, like just so that it's clear, this is a 2, right? I mean, z is with r, right? It's not with the 2. So if you divide by 2, you get r over 2 equals sine of theta, but that's not really z, right? Even if you were to compare with this equation.
Yeah, I meant in the r squared step.
Oh, okay. I see. You mean like
It'd be r squared over 2 equals r sine theta.
right. Yeah, this would be z, but only when you're finding the intersection between the plane and the cylinder, right? If you're not finding the intersection between the plane and the cylinder, they're completely separate equations. Is that making sense? Like, if you're trying, let me erase this like for a second. If you're trying to find like there's like a point, like there's some region where the plane, right, hits the cylinder, right?
Mhm.
And at that plane, at that region, like those points, which is actually like a curve, you can use both equations at the same time, right? But if you're not trying to find where like the plane hits the cylinder, then you cannot like mess around with the equations because they're two separate equations.
Okay.
Is that making sense?
Yeah, it's better.
Yeah. So I mean, what you're saying is correct if you were trying to find like where the cylinder and the plane intersect, because when you're finding out like an intersection, you can use both equations at the same time, right? But if you're just trying to find like if you're trying to find just like the equations separately, then you cannot like combine them. That's what I'm trying to say.
Okay.
Is that okay? Yeah, and the other part, like the other question is like, I just divided by r on both sides to get like the equation in terms of polar here. So those are like this is what happens with the two equations in cylindrical coordinates. And so let's try to find out the volume. Remember, the volume is like the integral. The volume is really the integral of dv. That's always the case, but it's just that dv in cylindrical coordinates is r dz dr d theta. Okay. And so again here, if you're trying to find the bounds for z, first, like what you're supposed to do is draw vertical arrows parallel to the z-axis. So imagine just drawing a bunch of vertical arrows here. So where do the arrows begin? What's the first bound for the arrows? They start on the XY plane, right? Oops. So here you put z equals 0. Is that making sense? And where do the arrows end? Yeah, they end at the equation of the blue plane. So they end on z equals r sine of theta. Okay. And then how are the bounds for r and theta determined? Again, you have to look at the shadow that this region makes on the xy plane. But what is the shadow in this case? It's just this, right? So let's try to draw this separately. So the shadow is just this circle of radius 1, center at the point 0, 1. And again, we saw that this circle had equation r equals 2 sine of theta. So how would you again, like that's the thing about this problem at this point. Like you totally forget about the 3D picture now, and you just focus on this picture. So what are the bounds? Think of it as a polar coordinate problem. What are the bounds here for r? Where does r start? Remember that in polar coordinates you have to draw arrows which are radial. So they will start at the origin, right? And where do these arrows all exit? They yes, they exit at the equation of the circle, which is 2 sine of theta. And this circle is located on the first 2 quadrants, so the angle goes from 0 to 2, from 0 to pi. Is that making sense?
Can you explain the first yellow disc pointing up to the plane one more time? What the actual disc to the left, where you were getting the arrows?
Right. So let me go to GeoGebra. Like you see, like the thing is like we're trying to find the volume, right? Well, because if you look at the statement of the problem, it says that you have to start, you're looking at the stuff above the XY plane, right? So this is, let's zoom in, yeah. Sorry, they should be parallel to the z-axis, but as you can see, that's a little bit tricky at this moment. But I think everyone gets like the picture. So I'm just drawing a bunch of arrows. I'm just drawing a bunch of arrows, right? In principle, parallel to the z-axis, correct? And you see they'll start from the XY plane, right? Oops, sorry, here it is. They'll start from the XY plane, right? And they'll exit through the plane, right? So that's why the bounds for z were from 0 to the equation of the plane, correct?
Right.
And then like I'm just saying, like you have to look at the shadow, but if you look at the shadow of this volume region, like it's again like imagine painting the roof with paint, like just redundant, but like you like the paint starts falling down, and then like what gets color is precisely this disc, right?
So are the vertical arrows in this case, these are representing z?
Yeah, the vertical arrows are representing the bounds for z. Okay. Yeah, but oops, looks a little bit deformed. What I'm trying to say is that after you find the bounds for Z, you have to look at the shadow the 3D region makes on the XY plane, right?
Mhm.
But like all the paint will just fall from the roof to the disk, right?
Right. Okay. I got it.
Is that making sense?
Yep.
And then like, okay, and so after you are convinced of that, like I'm saying, like you realize that for X and Y, or like you have to focus on this disk. And so I just draw like the disk separately because it's more convenient to see the bounds from here. This is the same disk. It's just like a copy of it as drawn separately. And then like before we had found the equation in polar coordinates for this circle, which was r equals 2 sine of theta. So that's why the bounds here go from 0 to 2 sine of theta. And then the bounds for theta, since this circle is in the first two quadrants, like theta just changes from 0 to pi. Is that okay? Yeah, it's 0 to pi just because the disk or circle is located in the first two quadrants. Is that making sense? And well, actually, this is sufficiently easy to do. So let's try to do this triple integral. So here you're integrating first with respect to Z. So there's nothing to integrate with respect to Z. So you get right, because like R is like a constant. So it's just R times Z. And now we have to evaluate. So you get like the integral from 0 to pi, 0 to 2 sine of theta. And then this just becomes R squared sine of theta. Good. Is that okay? So far, so good. And the R, sorry, I forgot the dr. And now we integrate this with respect to R. So you get the integral from 0 to pi. And then the R cubed over 3. R equals 0. R equals 2 sine of theta. And times sine of theta, right? Because we didn't like the theta, like sine of theta was like a constant. So you get the integral from 0 to pi of 8 thirds sine cubed of theta times sine of theta d theta. So you get the integral from 0 to pi of 8 thirds of sine squared sine to the 4 of theta d theta. Right? And so far so good. Is that making sense? And then, okay, obviously at this point, like some trig identity or something would have to be given to you because it's no, it's not. It's easier to integrate with the trig identity, and I don't remember like the trig identity for sine squared, so I'm googling it right now. If you, if not, I will just put it on Wolfram Alpha, or like yeah, like at this point, like let's see what Wolfram has to say. Yeah, but like you're not expected, I would say, to integrate like sine to the 4 without any help. So well, oh, you mean like, yeah, I mean they're like, right, it could be okay, yeah, right. I mean, again, not that like I'll let you like one thing, like again, like some, just to say, like one thing you could do is like that this is sine squared of theta squared, which seems obvious, but then like there's like this identity, which again, like you don't like, I mean, it would be given to you that like sine square of theta is, I think you may have seen it, like is 1 minus 2 minus cosine of 2 theta over 2. Okay, so I mean, something like the identity, I mean, again, like some help would be given, because like you may just be given like, but this is how you would find the identity for sine to the 4. And so this becomes 8/3 the integral from of 1 minus 2 cosine of 2 theta plus cosine squared of, I mean, it takes forever. So I mean, obviously, yeah, some trig, and again, you need to apply again, like here, like the trig identity. So like we won't focus too much in like there's like an identity for cosine square of some angle, but like let's just say that at least you should, like again, like something like an identity like this for the sine to the 4, I think is just too long. So it's not like, but if you had to integrate sine square or cosine squared, that's okay, because you would be given like the identity. But if you have to square that like just takes forever. So I'll tell you that if you put it on Wolfram alpha, all of this will give you 3 pi over 8. But I mean, like the point is that like it's not that you would I'm just saying, like you would not be expected to just integrate sine to the 4 without some sort of help, because like who remembers those things, right? And even sine to the 4 is probably a bit too much, but like so. Ooh, and that cancels the 8/3. That's cute, and then you get pi. Is that okay? I mean, but since we haven't done like an actual triple, like finishing like a triple integral, I thought like, okay, let's just finish this one. So you know the volume of that. Oh, like if this is volume, so this would be like whatever units you use, like pi cubic liters or pi milliliters or pi whatever, because it's what volume, right?
So then the input region, what dimensions does the input region have? Is it a 3-dimensional input or is it a 2-dimensional input?
No, the input itself was 3D because
Got it.
yeah,
and we also got a 3D output as well.
right.
Got it. Okay.
Yeah. Is this making sense? So far, so good. Now, actually, I sort of started like an example on cylindrical coordinates, which was kind of the hardest on the hard spec, like the harder side of the spectrum. Many times you will encounter some that are easier because they have symmetry. So let's talk about those cases. So And by symmetry here, I mean that theta does not appear in any of the equations describing the regions. So this by here by symmetry, I mean that theta does not appear any of the equations that you're given to determine the bounds. So notice, for example, that the case that we just did not have symmetry. Just sorry to go up for a second. This case didn't have symmetry because one of the equations involved theta, right? Theta was present in one of the equations, so there was no symmetry. And also here, like there was also a theta, so there was no symmetry. I mean, neither of them had symmetry. So the cases that we're going to talk about right now is when theta just does not show up. Okay. Good. And like the nice thing here is that if theta doesn't show up, then you can draw like a picture like on like what's known as the RZ plane. So in this case, you can find the bounds by drawing a 2D picture where the vertical axis is Z and the horizontal axis is R. So like what I'm trying to say is that you can draw a picture where here you put R and here you put C. So you can call this the RC plane. So let's try to work this out. Where R is the region Okay. So the first thing you need to do in all of these problems is find the region of integration. So let's try to figure this out. What's a cone? I mean, the equation, like a cone is a cone, like literally. So there were like some, I don't know if you remember, like there was this section 12.6 in the book where like some of these, you can find some pictures for these things. Like you can just check it out again if you want to know how they're supposed to look like. But I mean, sometimes like they're like, usually the word will be given to you of what this region represents. So a cone, like if it's called like a cone, it's usually because it's just like that. So this is how this looks like. Okay. And then you have the paraboloid. Paraboloids, like think of them as like if the word paraboloid is given, think of them as like salad bowls, kind of, or like, you know, something round. It is just like, like, you know, when the fact that x and y are 0, sorry, the fact that x and y are negative. Yeah, it's like a also it's like a 3D version of a parabola. That's also why it's called like a parabola. But the fact that x and y are negative means that instead of being like like you are placing it like normally on the ground, you just turn it upside down. So it's just something like this. Well, it is, I mean, like an apple size, you would think of it more as related to a sphere, because I guess people think more of like apples as being spherical, right? It is not, I mean, in terms of the picture I'm drawing, it's not that different, not that easy to distinguish the two, but like something like that is how a salad bowl is supposed to look like. Yeah, it's like a cone with it's like just like a curvy cone, basically. It like, let's go to GeoGebra. It is, let's see. So the first one was the cone, right? Z equals square root of x squared plus y squared. There you have it, right? That's a cone, right? And then the paraboloid was z equals 2 minus x squared minus y squared. And there you go. So you see there's like some region, like the region that I'm referring is like the stuff that's above the cone, right? So there's some stuff here which is above the cone, but below the paraboloid, right? Like you see what I'm getting at, like this thing in between the two surfaces. And that's like where the integral is taking place. So let me try to color it on the screen on iPad. Okay, so that's the region R. Is that okay with everyone? So far, so good? Now, again, after you figure out the region, what you're supposed to do is rewrite everything in terms of cylindrical coordinates. So let's start with the green one. How would this be rewritten in cylindrical coordinates? Again, that means to leave z as z, but write x and y in terms of polar, right? So what happens with the square root of x squared plus y squared? What does that become like in polar coordinates? Yeah, it just becomes r, right? So the equation, this equation in cylindrical coordinates is just z equals r, right? And what happens with this equation in cylindrical coordinates? Like again, a z remains the same. And so there's no, you just have to change x and y in terms of polar coordinates. So you get minus x squared minus y squared. What does that become in polar coordinates? Is that making sense? So if you notice, neither equation has theta. So like really the fact that not like what happens is that since neither has theta, you can think of this as a solid of revolution with respect to the z-axis. So you can sort of draw like a cross section essentially. So that's what I'm about to draw. So what is z equals r on this plane? That's like literally like the equation of a straight line, right? At 45 degrees. Like this is like y equals x. It's just that we're doing like using new names for them, right? But if you were to draw y equals x, you would draw like a 45 degree line. So that's the one that you draw here, right? Is that making sense? It's just like a linguistic thing, right? Because now the role of the vertical variable is being played by z and the horizontal variable by r, and z equals 2 minus r squared is like drawing y equals 2 minus x squared. So it is like a concave down parabola. Is that okay? So what I'm saying is that if you somehow imagine spinning this yellow cross section about the z-axis by 2 pi, you sort of recover the 3D region. Is that making sense? Like just imagine like grabbing that like and doing it like by 2 pi and you get back the full like volume stuff. And then just so that you know, like since r in cylindrical is always positive, that's why if there's only it's only necessary to draw the stuff on the positive r axis, right? So only since r is greater or equal to 0 in cylindrical coordinates, it is enough to draw only the stuff on the positive r axis. Is that making sense? Well, yes, let's try to set, like, now that we found the picture, let's try to like actually do the integral, which we have not done. Sorry. So what happens with this integral? Okay, so again, x becomes r cosine of theta, right? And remember that dz, dy, dx is like the volume stuff, is like dv, but dv in cylindrical coordinates is r dz dr d theta. Does that make sense? I mean, you don't have theta on the back, like you don't have theta on the equations for the surfaces, but theta still appears as like as part of the triple integral. Yeah, those are different things. And also notice that theta like does appear because of the function that you were given of what you're integrating, right? So because there's like an x here, and x depends on theta, you can like, you know, you cannot like forget about theta even if like none of the equations had theta, because like sometimes a function itself will have theta, and so it's always like a triple integral. Is that okay?
Can you explain again how we just got x as the integrand?
Oh, because it was an example, so I just like had to give some, like, this is like a random function that I gave you. Yeah.
Okay, thank you.
Yeah. It has no particular, it's just to make the integral sort of easy to do. Yeah. Is that making sense? Okay. And let's see. Anyone else? So far, so good.
Wait, so the r cosine theta, that was like from the problem, right?
That came from the problem, that came from the function that I put inside the integral from at the beginning. Yeah. It's just because I chose like to integrate x here that you have like r cosine of theta. Is that okay? If I had given you y, you would have put here like r sine of theta, right? Or like xz, you would have put like r cosine of theta times z. So yeah. That's why
Just a quick question. When it comes to figuring out the boundaries,
Mhm.
would one way be simpler than the other because of that intersection of the two curves?
Yeah, we're actually going to do it in both different ways, and you'll see that one is
Okay.
easier than the other. Correct. Yeah. But like the point that I'm making here is that thanks to the fact that that this sort of like none of the equations had like theta, you can sort of just focus on the 2D picture rather than going back to the 3D stuff. Well, it's just that this thing is dv, and dv in cylindrical coordinates is r dz dr d theta. But so far so good. Good. So again, if you are finding the bounds first in this way, you're using like arrows which are parallel to the z-axis. We still have that z-axis here, so let's try to put it. So what are the bounds for z? Where do the vertical arrows begin? They start at the green equation, right? And where do the arrows end? They end on the purple equation, right? So good. You put it here like z equals 2 minus r squared. And then what values for r should we use? And think of this almost like as doing like a, like psychologically, you should think of this like as doing like a double integral, like for dy dx. It's just that you're using new names for the variables, right? But yeah, the bounds for r are sort of like the bounds from 0 to the intersection. So we have to figure out what this intersection is. So when is r, what is this point on the intersection? Is when the z values are the same. So you need r to be 2 minus r squared, or 2r squared to be 2. And so that would happen when r equals r squared equals 1. So r equals 1. Oh, it's just that yeah, I can do it here. Like x squared plus y squared becomes r squared cosine square of theta plus r squared sine square of theta. And then you factorize an r squared and you get a cosine square plus sine square. And that's that becomes 1. Is that okay? Good. Yeah. Like you can also just write it like as a, feel free to just write it like as one of the formulas if you want. Is this okay? So like what I'm saying is that r, so here's 1. So here's a value 1. And so r has to go from 0 to 1. And theta, it would go from 0 to pi, right? Because it was a surface of revolution and it's in the 4 quadrants. So theta goes from 0 to 2 pi. Is this okay? So good. Any questions up to this point? Good. Right, when I calculated the intersection, well, I added r. Oh, sorry, this is, oops, because it was not r squared. Oops. Take it back. Let's do it again. Yeah, good. It was r equals 2 minus r squared. Good. So it's r squared plus r minus 2 equals 0. So this is what, like r plus 2 times r minus 1 equals, let me check. Is this better now? Good. So r equals, I mean, I made a mistake, but it was a mistake that didn't have like major consequences because it's still, you still got like r equals 1. R equals -2 is not allowed because, like, again, in cylindrical coordinates, these negative r's are not allowed. So the only option that really works is r equals 1. So far, so good. Well, it is just because if you look back at the original picture, you have to ask like how much, like imagine rotating this about the z-axis. So this piece, so how much, like what amount of angle do you have to rotate this to generate the entire 3D picture? So you know, like you have to do like a full revolution, like to be able to, like, you know, sweep out the 4 quadrants, basically. Is that making sense? And then just related to someone's question, you could say, okay, here I'm doing dz dr d theta, but you could also have done like, you could also have done the opposite order of integration. Which is like, dr dz d theta. So I'm just flipping, like, I'm switching z and r, the order in which they appear. If you do that, right, what happens, like, now you have to do arrows which are parallel to the r axis, right? And what's something that you can see from here if you use arrows parallel to the r axis? Anyone notices something? Yeah, you need to, right. You have to break it into two. So if you switch the order of integration, secretly you have to put like a second triple integral here. And I'm about to finish with this, so. So like, there's some arrows, some horizontal arrows that start where r equals 0, right? And they end on the green line, right? But now the green line is called r equals z, right? And then so I'm like, basically I'm breaking this. Let me do this more clearly. I'm breaking this along this black thick line, right? So well, good, hey, love, hey, good cop and bad cop type dynamic. So and then like the bounds for z in this case are, what's the value? The corresponding value for z is still 1. So z still goes from 0 to 1 here. And theta was not affected by reversing the order. So theta still goes from 0 to 2 pi. But let's look at the stuff above the thick segment. So it starts still when r equals 0, but now ends on the purple line. And the purple line now needs to be solved for r. So r squared equals 2 minus z, right? So r equals root of 2 minus z. Right? And then z, what are the bounds for z? Z goes from 1 to 2. And as I said, theta goes from 0 to 2 pi, right? So like something similar happens, which you also saw when you did the order dy dx, which is sometimes depending on which order you use, you end up with more than one integral, right? So in this case, if you had done dr dz, you just have to break it into two triple integrals. But like the point is that since there was no theta in either of the equations, you can sort of like find the bounds from like doing like a 2D picture. So that's better because keep to refer all the time to the 3D picture is a little bit more confusing. So this is more or less what you need to know about cylindrical coordinates. Next time we'll do spherical coordinates, which is the last thing for the exam. That one is a little bit more tricky because it does require you to change all the variables, x, y, and z. So we'll spend like Monday on spherical, and that's like the last topic for the exam. Okay, so I'll see you Monday of next week then. See you. You too. Bye. Oh, they're not.